Scene 1, Unveiling the Mysteries, the intersection of mathematics and spirituality. Welcome to a journey where the mystical and the mathematical intertwine. Today, we embark on an intellectual adventure to explore the surprising connections between two seemingly unrelated fields, Quranic architecture and the prime spiral sieve. In this series, we will delve into how both these disciplines, though originating from vastly different sources, one from the spiritual and the other from the scientific, employ numerical symmetries to uncover deeper truths. Quranic architecture examines the sacred texts of the Quran, interpreting its structure and the symbolic use of numbers to unlock divine patterns. Meanwhile, the prime spiral sieve, a sophisticated mathematical tool, sifts through the chaos of prime numbers to reveal an underlying order and symmetry. As we progress, we'll uncover how these patterns are not just coincidental, but are perhaps indicative of a more profound order that spans across cultural and disciplinary boundaries. Join us as we decode the secrets held within ancient texts and the very fabric of number theory, highlighting the universal quest for knowledge and the hidden symmetries that connect our world. Welcome to our exploration of numerical symmetry, where we delve into the fascinating comparison between Quranic architecture and the prime spiral sieve. Today, we uncover how both these realms, though rooted in different disciplines, religion and mathematics, reveal intriguing patterns and symmetries that guide their structures and insights. In Quranic architecture, scholars decode the intricate design of the Quran, seeking to understand its divine blueprint through numbers and patterns. This field draws upon religious texts, numerology, and symbolic interpretation to unearth a deeper coherence within the holy book. Conversely, the prime spiral sieve is a mathematical tool used by scientists to analyze the distribution of prime numbers. It employs techniques like modular arithmetic and computational algorithms to explore the secrets of number theory, revealing how primes are not as randomly scattered as they might seem, but instead follow specific symmetrical patterns. As we journey through this video, we will compare these two fascinating approaches to uncovering hidden orders in their respective domains. We will explore their origins, methodologies, and the significant patterns they reveal, such as the use of number 19 in the Quran and the interval symmetries in prime distributions. Join us as we bridge the gap between the spiritual and the quantitative, highlighting how both fields, though seemingly disparate, share a common quest for understanding the underlying order of our world through the lens of numbers. Imagine a world where nature and numbers intertwine in a dance of symmetry and structure. A world where interval symmetry, the concept that the same musical intervals can be found starting on different pitches, opens up a symphony of mathematical harmonies. A world where the Archimedean structure, an ordered architectural masterpiece constructed from regular polygons, marries the worlds of geometry and mathematics. In this world, prime numbers, those indivisible by anything other than one, and themselves, play a starring role. And Fibonacci sequences, numbers in which each is the sum of the two preceding ones, also take center stage. Here, we witness the Fibonacci terminating digit symmetry, a fascinating phenomenon where the last digits in the Fibonacci sequence repeat in a predictable pattern, painting a rhythmic pattern on the canvas of numbers. Come along as we embark on a journey through the mathematical beauty and explore these intricate wonders of the prime spiral sieve. Welcome to this mesmerizing world of number patterns. Journeying into the core of our exploration, we stumble upon the concept of interval symmetry. This is where an enchanting pattern emerges from a periodic difference sequence between prime roots. With a harmonious rhythm, the entire domain pulsates to an endless repetition of the sequence 1 plus 6 plus 4 plus 2 plus 4 plus 2 plus 4 plus 6 plus 2. As we delve deeper, we discover the number 30 making its grand appearance. This number is not just a mere integer, it holds a paramount significance in this modulo 30 domain, emerging as the key player around which the sequence revolves. It is the fundamental entity that sets the rhythm and directs the dance of this mesmerizing number pattern. But the beauty doesn't stop there. Our journey next to the Archimedean structure, where the prime spiral sieve showcases a remarkable feature, a consistent separation distance of 30 between each turn. This meticulous spacing continues as the structure spirals into infinity. Intriguingly, the sum of the second rotation within this structure amounts to 360, showcasing a fascinating numerical symmetry embedded in its design. Exploring further, we find the captivating property of Fibonacci numbers, their terminating digits. When indexed, these digits link together to form a prime number, specifically 13,937,179. Intriguingly, this prime number is part of a twin prime pair, closely associated with another prime number, just one apart. This unique pairing showcases the interconnectedness and the hidden mathematical harmony within the Fibonacci sequence. Our investigation into numerical patterns uncovers a fascinating example of palindromic equivalency. Specifically, when you take the number 13,937,179 and reverse its digits to get 17,179,933, and then sum these two numbers, the result is a striking 111,111,110. As we transition from the intriguing world of Fibonacci sequences and palindromic numbers, let's explore a concept that intricately ties together prime roots and their reversals, revealing yet another layer of symmetry in our mathematical tapestry. Consider the prime roots we've discussed earlier. When these numbers are reversed, they don't just stand as a mirror image, they transform into new entities with their own unique properties. For instance, take the prime root 17,137,939. Its reversal, 93,973,171, isn't just number, it's a semi-prime. This means it's a product of two primes, specifically 9,461 and 10,271. What's more fascinating is the sum of 17,137,939 and its reversal, which equals 111,111,110, resonating with the palindromic sum we observed earlier. This phenomenon isn't isolated. The terminating digits of prime root angles, such as 24,064,868, and its reversal, 86 and 846,242, also sum up to the same palindromic number, 100,111,110. This repetitive emergence of the number 111,111,110 across different mathematical constructs not only highlights a deep-seated symmetry, but also suggests an underlying connection that binds these elements together in the realm of number theory. By examining the properties of these reversed numbers, we uncover a layer of complexity within the prime roots, suggesting that each number holds a hidden narrative that unfolds through its reversal. This interplay between numbers and their mirrored counterparts adds a rich texture to our understanding of numerical symmetries and primes, further emphasizing the elegance and interconnectedness of mathematical structures. Next, we delve deeper into the intriguing pattern shared by the terminating digits of the first 8 Fibonacci numbers and the first 8 domain members. Both sequences display a recurring pattern where the digits 1, 3, 7, and 9 appear in a specific cyclic order. This pattern not only highlights a numerical symmetry, but also suggests a deeper mathematical harmony between these two seemingly unrelated series. Our exploration leads us to an astonishing revelation. The ultimate combinatorial symmetry unveils itself when we merge the terminating digit symmetries from 3 distinct rotations, revealing that their combined reversals astonishingly sum up to 111,111,110. This perfect symmetry marks a significant discovery in our journey. Finally, we explore how the decomposition of Fibonacci numbers and the examination of prime root angles uncover fascinating digit sum patterns, adding a profound depth to the intricate mosaic of mathematical elegance. As our exploration concludes, we're left in awe of the elegance and complexity of the symmetries we've discovered. These intricate patterns reveal the deep connections between number theory, geometry, and symmetry, and stand as a testament to the richness of mathematical structures. A world where prime numbers and Fibonacci sequences dance together in a symphony of mathematical beauty, that's the world of the prime spiral sieve. Delving deeper into the mathematical tapestry we've uncovered, let's focus on the periodic difference sequence between prime roots and the intriguing role of the number 30 in the modulo 30 domain. As we've seen, prime roots exhibit a fascinating pattern when examined under the lens of modulo 30. This specific domain not only simplifies the complex structure of primes, but also reveals a balanced, repeating pattern that extends infinitely. In this domain, the differences between consecutive prime roots show a periodicity that is both unexpected and enlightening. This periodic difference sequence isn't just a random occurrence, it's a symphony of numbers playing out across a predefined stage set by the number 30. Why 30, you ask? 30 is a highly composite number, which means it has more divisors than any number smaller than it. This property makes it a prime candidate for revealing symmetrical patterns in numbers, especially primes. As we chart these differences, a clear pattern emerges, one that repeats itself in a cyclical fashion. This repetition isn't merely a curiosity, it's a window into the underlying structure of the number system itself. It suggests that the properties of primes are not as chaotic as once thought, but are governed by hidden rules that resonate through the fabric of mathematics. This exploration not only deepens our understanding of prime numbers, but also enhances our appreciation for the subtle and often hidden symmetries that govern the universe of numbers. As we continue to unravel these patterns, we edge closer to unlocking the secrets of mathematical harmony. As we journey further along the prime spiral sieve, an intriguing aspect comes to light: the consistent separation distance of 30 between each turn in the spiral. This distance is not a mere coincidence, but a profound reflection of the sieve's underlying mathematical structure, which extends infinitely. Each rotation around the spiral marks a significant step in understanding the distribution of prime numbers. Now, let's delve into the sum of the distances in the spiral's rotations. On completing the second rotation of the spiral, an extraordinary fact surfaces. The total sum of these distances equals 360. This number isn't arbitrary. It is deeply rooted in the foundational blocks of mathematics, being the product of the first three primorials, 2, 3, and 5. Multiplying these gives us 30, and extending this to 12 rotations results in 360. This relationship highlights a beautiful symmetry and interconnectedness in the structure of numbers, especially primes. The number 360, known for its ubiquity in geometrical contexts such as the degrees in a circle, here finds a novel significance in the realm of number theory through the prime spiral sieve. This not only enriches our understanding of prime numbers, but also bridges concepts across different mathematical disciplines, suggesting an elegant uniformity underlying apparent complexities. As we appreciate this seamless integration of prime theory and geometric symmetry, we are reminded of the endless wonders that mathematical exploration brings. The prime spiral sieve is not just a tool for finding primes, but a gateway to deeper insights and a greater appreciation of the universal patterns that bind the world of numbers. Building on the fascinating insights from the prime spiral sieve, let's now explore an equally intriguing numerical interplay involving Fibonacci numbers and prime reversals. As we know, Fibonacci numbers are a sequence where each number is the sum of the two preceding ones, starting from 0 and 1. What happens when we index Fibonacci numbers to a domain that forms a prime number, its twin prime pair, and examine the semi-prime nature of its reversal? Consider Fibonacci numbers whose indices are prime numbers. These Fibonacci primes, as we might call them, carry the mystique of both Fibonacci and prime number properties. Now let's extend this concept to twin primes, pairs of primes that are as close as possible, being only 2 units apart. When Fibonacci numbers are indexed by twin primes, they reveal a fascinating pattern. Often, one of the Fibonacci numbers indexed by a twin prime is itself prime or exhibits prime-like properties. The plot thickens when we reverse these indexed Fibonacci numbers. A number is termed semi-prime if it is the product of exactly 2 prime numbers. Intriguingly, when we reverse the digits of many Fibonacci numbers indexed by prime numbers, they transform into semi-primes. This reversal adds a layer of complexity and symmetry, weaving a delicate dance between the sequence's inherent numerical properties and prime theory. For instance, take the Fibonacci number at the 11th position, which is 89, a prime number. Its twin prime counterpart at the 13th position is 233, another prime. Reversing 89 gives us 98, which is not prime but semi-prime, being the product of 2 and 49. Similarly, reversing 233 gives us 332, also a semi-prime, 4 and 83. This dual nature of Fibonacci numbers and their reversals offers a rich tapestry of mathematical relationships to explore. As we dive deeper into the numerical ballet of Fibonacci primes, their twin pairs, and the intriguing semi-prime reversals, we uncover layers of symmetry and structure that challenge our understanding of both number sequences and prime theory. This exploration not only highlights the interconnectedness of different mathematical domains, but also underscores the beauty and complexity inherent in the world of numbers. Transitioning from the mesmerizing dance of prime-indexed Fibonacci numbers and their semi-prime reversals, we now delve into another captivating numerical phenomenon, the sum symmetry of a number and its reversal within the Fibonacci sequence. This exploration showcases how, intriguingly, the sum of a Fibonacci number and its reversed counterpart often leads to specific repeating sums, revealing a hidden layer of symmetry in the sequence. Consider the Fibonacci sequence as it extends infinitely. Each number in the sequence, when reversed and added to its original form, frequently results in sums that exhibit a pattern or repeat specific values. For instance, let's analyze the Fibonacci number at the 21st position, which is 1946. Reversing the digits, we obtain 64901. Adding these together yields 75847, a number that doesn't immediately reveal any obvious patterns. However, as we expand this examination across more Fibonacci numbers, a startling symmetry emerges. Certain sums recur with surprising regularity. To deepen our understanding, let's perform a broader analysis by summing numerous Fibonacci numbers with their reversals. Interestingly, we observe that these sums often converge to multiples of a specific number, demonstrating a consistent pattern across the sequence. This phenomenon is not just a trivial observation, but underscores a deeper mathematical structure within the Fibonacci series, suggesting an underlying rule or principle governing these sums. Moreover, when we extend this analysis to the entire repeating Fibonacci sequence, the cumulative sum of all numbers and their reversals also converges to this recurring sum, tying back beautifully to the concept of infinite extensions and summation symmetry discussed earlier in the prime spiral Sieve. This remarkable consistency across such a diverse and complex sequence not only highlights the inherent beauty of mathematics, but also challenges us to ponder the deeper connections between number theory, symmetry, and sequence behavior. As we continue to explore these fascinating numerical relationships, we uncover more about the intricate tapestry that is the Fibonacci sequence and its interaction with the concept of reversals, further enriching our understanding of mathematical symmetries and their implications. Venturing deeper into our numerical odyssey, we now turn our focus to the mysterious and compelling world of terminating digits within both the Fibonacci sequence and the prime roots. In this segment, we explore how the terminating digits of Fibonacci numbers often share intriguing patterns with members within specific mathematical domains, especially when we examine the sum of prime roots terminating digits with their reversal. Let's begin by observing the Fibonacci sequence, particularly concentrating on the last digits, or terminators, of each number. For instance, take a close look at a segment of the sequence, 583145. Here, the pattern of terminating digits starts to repeat every 60 numbers, a cycle linked to the properties of modulo 10 arithmetic. This cyclical nature hints at a deeper symmetry, possibly connected to the inherent properties of the sequence itself. Now, consider the prime roots, fundamental components in the structure of numbers. When we analyze the terminating digits of these roots and sum them with their reversals, another layer of pattern emerges. For example, if a prime root ends in 7, its reversal ends in 7 as well. And summing these, we consistently get sums ending in 4 or 9, depending on the adjacent digits. This consistent result across various prime roots suggests a robust symmetry in the arithmetic landscape of these numbers. To illustrate, let's perform a comparative analysis. Taking a prime root, such as 17, and its reversal 71, the sum yields 88, where the terminating digit is 8. When mirrored with Fibonacci numbers like 21 and digit 1 and its reverse sequence counterpart 12 and digit 2, their sum also prominently features the terminating digit 3, echoing the symmetry observed in prime roots. This exploration not only enriches our understanding of the Fibonacci sequence, but also bridges connections with the prime roots, revealing a shared pattern in their terminating digits. Such discoveries are more than mere numerical coincidences. They represent the underlying mathematical harmony that governs these sequences. As we continue to uncover these patterns, we delve deeper into the mathematical tapestry, revealing the intricate and often beautiful symmetries that form the backbone of number theory. As we continue our exploration of numerical symmetries, let's delve into an even more nuanced aspect: the terminating digits of prime root angles and their reversals. This fascinating phenomenon not only highlights the inherent patterns in prime numbers, but also adds a geometric dimension to our understanding of numerical symmetries. Consider the angle formed by a line segment connecting the origin to any prime root on a circular plot, where each point represents a prime number plotted at a distance equal to its value from the origin. The angle, measured in degrees or radians, typically terminates in digits that, when reversed, reveal an unexpected regularity. For example, if a prime root angle terminates in 3 degrees, its reversal would be an angle ending in 3 degrees when measured from the complementary 360-degree perspective. Adding these angles, 3 plus 3, we consistently find that sums terminate in a specific digit, often reverting back to 6. This intriguing result is not arbitrary, but is a reflection of the underlying modular arithmetic governing these angles. To illustrate this, let's take a closer look at a series of prime root angles: 43, 83, 123, and so on. Each of these angles, when reversed, adds up to numbers whose terminating digits form a predictable pattern, often culminating in 6. This pattern is not just a curious coincidence, but a testament to the symmetrical properties inherent in the spatial distribution of prime numbers. This angular symmetry is not merely a mathematical triviality, but hints at deeper laws of distribution and balance within the number system. It challenges us to think about numbers not just as quantities, but as elements that carry both spatial and numerical properties. As we compare these findings with the earlier discussed symmetries in Fibonacci sequences and prime roots, a beautiful picture of interconnectedness emerges. These patterns found in the terminating digits and their sums underscore a universal harmony in mathematics, manifesting across different systems and scales. Join us as we continue to unravel these patterns, enhancing our appreciation of the elegant and often hidden relationships that make mathematics a perpetually intriguing field. In this next segment, we're going to explore the emergence of ultimate combinatorial symmetry when combining terminating digit symmetries from 3 rotations. This is a fascinating extension of the angular symmetry we've discussed in the previous scene. Imagine, if you will, that we are looking at 3 rotations, each based on the terminating digits of prime root angles and their reversals, as we did before. Let's call these rotations R1, R2, and R3. When we combine these rotations in a special way, a new and exquisite pattern begins to emerge. For each rotation, let's consider the terminating digits of the angles involved. For instance, if R1 ends in 3, R2 ends in 7, and R3 ends in 5, we can add these digits together. The sum of these digits, in our example 15, also has a terminating digit, in this case 5. Now let's perform this operation for a series of rotations. You'll notice that the terminating digits of these sums begin to form a sequence. And this sequence, astonishingly, manifests an ultimate combinatorial symmetry. These symmetries are not random, but rather they reveal a deeper underlying structure within the world of numbers. They hint at a hidden order, a mathematical harmony that permeates through different domains, from prime roots to Fibonacci sequences, and now to rotational terminations. This ultimate combinatorial symmetry is yet another testament to the intricate beauty that lies within the realm of mathematics. It's a vivid illustration of how numbers, when viewed through the lens of symmetry, can unfold in patterns of surprising complexity and elegance. In the next scene, we will continue our journey into the fascinating world of numerical symmetries, discovering new patterns and connections. Stay tuned. In this segment, we're going to delve deeper into the world of numerical symmetries by investigating the intriguing digit sum patterns that arise when we decompose Fibonacci numbers and prime root angles. Let's begin by taking a Fibonacci number, say f, and a prime root angle, let's call it p. Now, decompose both f and p into their individual digits. For instance, if f is 89 and p is 37, we would decompose them into 8, 9, and 3, 7, respectively. Now, let's add up these digits. For our examples, the sums would be 17 and 10. Notice anything interesting? The sums themselves, 17 and 10, also decompose into individual little digits that, when added, create another layer of intriguing digit sum patterns. The beauty of this approach is that it isn't confined to any particular Fibonacci number or prime root angle. You can pick any Fibonacci number, any prime root angle, decompose them, add up their digits, and you'll find this pattern emerging again and again. And if we map these digit sums, they form an incredible pattern, a symmetry that is both captivating and profound. This tells us that even when we break down numbers to their most basic components, their individual digits, there are still fascinating patterns and symmetries to discover. It's like peeling back the layers of an onion, each layer revealing a new, intricate pattern that reflects the inherent beauty and complexity of mathematics. In the next scene, we will further explore these fascinating patterns, revealing even more about the intricate connections within the world of numbers. Stay tuned.